All right, guys. So here's the first problem for today. We got Sally. She's got a mass of 50 kilograms, and the Earth, it's got a slightly larger mass of 5.98 times 10 to the 24th kilograms. They are both pulling on each other. They always are. Any two things that have mass are always going to pull on each other. We know the radius of the Earth. In this problem, the radius means the distance from the center of the Earth to the center of what? Sally. That's what that radius means. We want to find the force of gravitation between Sally and the Earth. To do that, we're going to have to use Newton's law of what? Universal gravitation, which we learned about yesterday. Let's put that equation. I'll give you the problem in a minute. Let's put the formula up here first. F equals G M1 M2 over what? R squared. You also need to know what G is. Remember G, before they figured out what G was, this equal sign was a proportional sign, right? And then they figured out the number here that would make them be equal instead of proportional. And that G is always 6.67 times 10 to the negative 11. And that is going to be equal to what units? There we go. Newtons times meter square all over kilogram square. So let's plug in what we know. We know that F equals G. We're going to put in G. All right, and then we need the M's are the masses. So we need Sally's mass, we need the Earth's mass, and I'm going to have to backtrack to get that. So Sally was 50, and the Earth was 5.98 times 10 to the 24th. All right, and the radius, the distance between Sally's center and the Earth's center, 6.37 times 10 to the 6th, and that's in meters. So let's go back. So let's put in mass 1. We'll call mass 1 Sally. And we said that was 50. Let's multiply that by the Earth's mass. I'm going to move that out of the way. Put in the mass of the Earth, which was 5.98 times 10 to the 24th. And let's divide that by the square of the radius. Now the radius was a big number. 6.37 times 10 to the 6th. And that's meters. And we have to square that whole thing. The hardest things in terms of working these problems is to get it in your calculator the right way. So let's try to put this in the calculator and see what we get. I'm going to go ahead and just do the top first. I'm going to go 6.67 times 10 to the minus 11 times 50 times 5.98 times 10 to the 24th. And on the top, I'm going to go ahead and write down what I got on the top in case I screw something up in my calculator. 1.99 times 10 to the 16th. That's what I get on the top. I'm going to divide that by the bottom. I'm going to go ahead and go 6.37 times 10 to the 6th. And then I'm going to square that. What I get on the bottom is this. So when I divide those out, let's see. And I just messed it up. Let me try that again. 1.99 times 10 to the 16th divided by 4.06 times 10 to the 13th. And I get 490. So 490 with a decimal place because we had 3 significant digits. And if you look at your units, kilograms squared right here, cancel with kilograms and kilograms. Meters squared right here are going to cancel with meters squared right there. So we're just left with newtons.
Yeah.
Makes sense because we're looking for what? Force. The force of gravity. Now, sometimes this law of universal gravitation is called the inverse square law, because the force of gravity varies with the what? With the inverse of the square of the radius, the distance between the two things. All right, we will stop there. But before we do, one more quick point before we stop. The second part of this equation was to find the weight of Sally.
It's the same.
We could have found the weight by going what? M times G and gotten exactly what? The same answer.
So we're trying to determine the gravity force.
All right, next problem, guys. Number 14 up here on the sheet is this problem about Jupiter. Now, this is one where we're going to have to use one of Kepler's laws. Now, just in review, Kepler had 3 laws of what are called planetary motion. The first one, he figured out that the planets didn't go in circles around the sun, but instead ellipses. He also found out, secondly, that as the planet gets closer to the sun, what happens to it? It speeds up. As it gets further away, it slows down. In the video we saw yesterday, he did a good job of explaining it because he compared it to what? A ball in what kind of motion? Projectile motion. That as it's going up, it's slowing down, and as it heads back, it starts to what? Speed up. It's going its fastest when it leaves and when it what? Comes back. It's a good analogy for Kepler's second law. Now his third law is an equation, and that's the equation we're going to have to use to work this problem. But let's read the problem first, and then we'll put it up here. Jupiter is 5.2 times further than the Earth is from the Sun. Find Jupiter's orbital period in Earth years. Got to enunciate a little bit there. First of all, how far is Earth from the Sun?
180.
Yep. Joe said 1 AU, 1 astronomical unit, equivalent roughly to about 93 million miles. So we got to know that to work the problem. So let's go to a blank slide where we can set this up. Now we're trying to find the period of Jupiter. So here's the deal. Kepler's third law basically says this, that the period of a planet, like so, the square of the periods of both of these planets is equal to the ratio of the radii of those planets cubed. That's essentially Kepler's third law. So in this problem, it doesn't matter which one I call A and which one I call B as long as I'm consistent. But I'm going to call A Earth and B Jupiter. So for this problem, first of all, the period of Earth. What are we going to put in for the period of Earth? 1 year. It takes 1 year to go around the sun, right? So we're going to put in 1 year for that. Going to go ahead and square it. The period of Jupiter is what I'm trying to find. I'm not sure exactly what that is. The radius of Earth, now I could put in lots of different things. I could put in 93 million miles. But this says to find Jupiter's period in units of what? The Earth's, we're trying to do it in terms of the Earth stuff. So it would make sense to put what in for the radius? 1 AU. Cube that. And it tells us in the problem that Jupiter is 5.2 times further from the Sun than Earth is. So for the radius of Jupiter, I'm going to put in what? 5.2 AUs. 5.2 times further. And again, I got to cube that. So we got to do a little cross multiplication. So if we cross multiply this way, we're going to have 1 AU cubed times TB squared equals, now let's cross multiply that way, Let's cube 5.2. That is 140, I'll just say 141. So it's going to be 141 AU cubed times 1 year squared. Now we're trying to solve for TB. So let's first of all divide this out right here. That's just going to cancel the AU cubed right here. And then we just got to take the square root of both sides, right? So take the square root of 141, and we get about 11.9. What that is telling us is that it's going to take Jupiter about 11.9 Earth years to go around the sun. 1 Jupiter year is 11.9 Earth years. Does that make sense? All right, so let's backtrack. Let's go ahead and try 15 too. 15, a satellite is placed in orbit with a radius that is half the radius of the moon's orbit. Find its units. Find its period in units of the period of the moon. Now, there's several ways we could do this. One way is to use Kepler's third law. Let's do it that way to begin with. So let's go in here. Put back up Kepler's third law so we don't forget what it is. TA squared over TB squared equals RA cubed over RB cubed. This works as long as the two things you're talking about are doing what? Orbiting what? The same thing. Could be two planets orbiting the sun. It could be two satellites orbiting the Earth, which is what this is, right? The moon and an artificial satellite orbiting the Earth. Now, the problem says a satellite is placed in orbit with a radius that is half the radius of the moon's orbit. Find its period in units of the period of the moon. So it doesn't give us any numbers. So how are we going to work this problem? Yep. So there's two ways we could do it. There is a table in your book that lists all the radii of things. You can go look it up. You could physically go look up the distance between the moon and the Earth, and you could use that. It's not the easiest way to do it, though. Let's do it this way. For the period, we're going to call A the moon and B the satellite. So for A, what do you think I ought to call the period of the moon? I'm just going to call it 1. I'm going to call it 1 moon. How about that?
Yeah.
Okay. 1 moon.
1 new moon.
And I'm going to square that. So I'm going to have a moon squared. All right. For the period of the other thing, that's what we're looking for. Is we're looking for the period of the satellite. So we're looking for TB. The radius of the moon. What am I going to put in there? 1. Again, I could make up a unit if I wanted to, but I'm just going to call it 1 radius for right now.
And we put for the bottom 1.5.
Yep. Now the bottom one, it says its satellite its radius is half the moon's radius. So I'm going to put in a half radius here. But I have to cube that. So now let's do a little cross multiplication. Let's go this way first. So that's going to give me TB squared times radius cubed. I'm just going to say rad cubed. All right, then let's cross multiply this way. That's going to give me a half times a half times a half, 1/8. 1/8 rad cubed times the moon square, right? All right, we're trying to solve for TB square. So we divide both sides by that radius cubed. Get rid of that. That's going to cancel. So basically, to find our answer here, we just need to take the square root of 1/8, right? So let's go 1 divided by 8. And then let's take the square root of that. And we get about 0.354. So that equals to 0.354, and my unit would be moons here, right? Which means the period of the satellite is a little more than a third the period of what? Earth. The moon. It's a little more than a third. By the way, what is the period of the moon? That's what a month is based on, right? It's actually like 28 days. So this is somewhere around 10 days. Period. It would take this satellite about 10 days to go around the Earth. Period of the moon is 28 point something days. That's about a month. Questions? Let me pause for a second. All right, here we go. Number 16. Hey, number 16. A satellite has an orbital radius of 4.23 times 10 to the 7th meters. What is its speed in orbit? Also find its period. Here's one where you got to think a little bit. I'm going to leave this problem up for a minute. When a planet is, or satellite in this case, is orbiting a planet, what makes it go in that orbit? Gravity is acting like a centripetal force. To work this problem, you got to know that. You're going to have to set those two equations equal to each other. Universal gravitation equal to centripetal force equations. So let's go to the other slide, and let's do that work first. I'm recording all of it. And we're going to derive a formula.
Are you recording now?
Yes. So we're going to set equal, in the case of any two things that are orbiting, that's force of gravity equals centripetal force. And we're going to set those two equations equal to each other. So for gravity, we know it's G times what? We're going to say mass of satellite times mass of what? In this problem, what's the satellite going around? It doesn't say. We assume it's a planet of some kind. We'll just say mass of planet. All over what? The radius squared, which is the distance between these two things' centers. That's got to be equal to centripetal force. What's our most basic equation for centripetal force? mv squared r. And remember, that's no different than m over what? M times what? V squared r is acceleration. So this is Newton's second law. I told you Newton's second law is the most important idea in physics. Here it is again. We saw it when we were doing torque. We saw it now when we're spinning things around. It's everywhere. Can't get away from it. What is this the mass of, though, in this equation? It's the mass of the thing that is orbiting. So in this case, it's the mass of the satellite. We're trying to find the period. What is the speed of this thing in orbit, and what is its period? So again, the problem was the satellite has an orbital radius of 4.23 times 10 to the 7th meters. What is its speed in orbit? Find its period. Now, one thing we do need to know, and I should have put in this problem, is what it's orbiting. It doesn't say that in the problem. We're going to assume it's orbiting what? Earth. The Earth. What are we going to need to know about Earth? We're going to need to know the mass of the Earth. And if you remember in a problem we worked just a minute ago, we had that. It's the 5.98 times 10 to the 24th. So let's go back and do a little math on this. Let's first of all multiply both sides by r. Because what are we trying to find here? First, try to find the velocity. So let's multiply both sides by r. When we do that, that's going to cancel this out. It's going to take off that squared there, like so. Now let's divide rather both sides by the mass of the satellite. When we do that, you can see it cancels here, and it also cancels here. So that now you should be able to see, to find the velocity, we need to take the square root of both sides. And what we end up with is that equation. And I'm going to ignore the phone right now, so let's just keep working. So to calculate the velocity of this particular satellite, plug in what we know. G, 6.67 times 10 to the minus 11. And remember, the units are newtons times what? Meters squared all over kilograms squared. We've got to multiply that, in this case, by the mass of the planet, which is Earth. And that's the 5.98 times, yep, 10 to the 24th it is, kilograms. And then we've got to divide that by the radius, which is also given to us in the problem. The radius was 4.23 times 10 to the 7th meters. And we've got to take the square root of that whole thing. Now again, the hardest part of a problem like this is getting it in your calculator the right way. Let's take a minute and try to get that done.
Just wrap it into creates on the fraction. On mix of light.
Oh yeah, you can do it. Let's go to 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24th divided by 4.23 times 10 to the 7th. And then I'm going to take the square root. And you guys check my math here. But what I'm getting is 3,070. Actually 71. And I think in this problem I need 3 significant digits. Yep.
Yeah, we got stuff correctly.
So I'm going to say 3.07 times 10 to the 3rd. Now, I want you to pay attention to the units on this. Just a minute. Pay attention to the units. Kilograms here are going to cancel. Like that. These meters going to cancel right here, leave a meter behind. Now right now we've got newtons, meters, and kilograms. That doesn't make much sense. What you got to remember is that what is a newton? Kilogram times a meter per second square. So what I'm hoping that you see is that we've got newtons times meters, so this is actually going to square up. And the kilograms are going to what? Cancel out. So we end up with meters squared over second squared before we do what? Before we square root it. So our units come up to be meters per second. So in this problem, we get 3.07 times 10 to the 3rd meters per second. Let me get Paul for a time. Board. All right, guys, one thing that we didn't do, we didn't find the period for problem 16. Found the speed. Our speed, since I've erased the work there, what was the speed again, guys?
3070 meters per second.
I got 3 points.
Yeah, so it was 3,071 meters per second.
And I got something slightly different entirely.
Oh, we'll work on that in a minute. Let's do this right now. All right, let's find the period. Same numbers. Let's go to a new slide. This is another one of these situations where we're going to have to derive an equation. We're going to have to take, again, the force of gravity equal to what? Centripetal force. All right. Now, again, we know the force of gravity is G times the mass of the satellite times the mass of the Earth all over the distance between them squared. That's equal to M. V squared over R. And remember, this mass is the mass of the satellite. But you don't see period up there right now, right? We're trying to find a period. We're going to have to make a little substitution. And what we're going to substitute for is right here. When we're talking about centripetal velocity, the centripetal velocity can be found using that equation. But remember, this was v squared over r. So that has to be squared. Now we're going to have to do a little math. This is going to be a little tougher.
Yeah.
So we're going to go g times ms times me all over r squared equal to ms. We've got to square this, so that's going to be slow down. 4 pi squared r squared over t squared all over r. So that's a lot of math. Now, before we go further, let's figure out what we can cancel out. This r right here on the bottom of the fraction is going to flip up, and it's going to cancel out one of those, right?
That's going to be multiplied by one of those.
No, this is like r over 1. So to simplify it, we have to invert and multiply, so it's going to end up down here on the bottom of the fraction.
Last time you did it, we had an R cube.
Yeah, it should be the other way around. It should be the top number over 1, and then t squared over r, and then you flip that.
No. If I did it that way, I messed up. This is like r over 1. When you have a fraction divided by a fraction, you have to invert and multiply. So it's going to be like this. It's going to be like times 1 over r. Which means this should cancel. And I may have messed that up if I worked it before. I don't know. But one of those cancels out. Now, we're trying to solve for period. So the first thing I'm going to do to solve for period is get that period off the bottom of that fraction. So I'm going to multiply both sides by t squared. So my t squareds cancel over here. And now I got to get rid of all of this stuff. To get rid of all that stuff, I need to multiply by its what? By its inverse. So I need to multiply both sides by r squared over g ms me. When I do that, that gets rid of all this gunk over here. And if we do a little simplifying on this side, the MS's cancel out. That's all that cancels out. The r's become r cubes.
What happened to the t squared again?
It was on the bottom of the fraction over here on the right. I multiplied both sides by it, so it came up over here on the left.
So it's just up there.
There's that t squared. T squared is equal to all this. And I'll rewrite it out in a minute, but let's go ahead and rewrite it out now. So my equation is t squared equal 4 pi r cubed all over g times me.
Where did the square go?
Where did the square go?
Square's still there.
Pi squared.
4 pi squared over r cubed over GME. There you go. It just disappeared for a minute. It's taking a break.
Okay, how much is their play?
5.98 times 10 to the 24. But hold that, we'll get there.
Yeah, I got something else entirely.
Record this right now. You gotta just bear with me. We're going to take the square root of both sides. When we take the square root of both sides, we end up with t equals. We can take the square root of the 2 and the pi squared. So we get 2 pi. The rest of that stuff we can't really get a square root of. So we can write it this way. This equation, or this equation, either one, those are sometimes called what equation?
Crazy. Weird.
There's a name for that equation.
Derived.
They are called Newton's version of Kepler's third law. Newton's version of Kepler's third law. That's that equation.
Remember that. Remember that.
I think I'm going to make you figure that one out.
That's so mean. That's long.
Anyway, now we've got to work this thing. So all we really need to know to work the problem is the radius between the satellite and the Earth and the mass of the Earth. And we got that. So, let's plug it into our equation. T squared equals 2 pi times the square root. Oh, sorry, T. T equals 2 pi times the square root of the radius cubed. The radius in our problem was 4.23 times 10 to the 7th meters. We got to cube that. All of that is divided by G times ME. Again, I'm going to have to make a little space here. Remember that G is our universal gravitation constant, the 6.67 times 10 to the minus 11. And the mass of the Earth, 5.98 times 10 to the 24th kilograms. Well, let's see. Let's do the math on this. Let's go 4.23. 24. 4.23 times 10 to the 7th. Let's cube that. All right, then let's divide that by 6.67 times 10 to the minus 11. Let's divide it again by 5.98 times 10 to the 24th. And then finally, let's take the square root. Actually, not finally, we got something else to do. Then we got to multiply that by 2 pi. So let's go ahead and multiply it by 6.28. And when we do that, we get a big number. We get about 8.65 times 10 to the 4. And let's think about the units on this. Slow down. Think about the units for a minute. Right now, we've got meters squared right here, meters cubed up here. Cancel, cancel, leave behind a meter. We got kilograms squared here, kilograms here. Cancel, cancel, leave behind a kilogram. Now what you got to remember, again, you got to remember that a Newton is a kilogram times a meter all over second squared. So if you remember that, you should see that the kilograms are going to cancel, the meters are going to cancel, and what's going to be left?
Nothing.
The second squared part. And what are we doing to the second squared part? We're taking the square root. So this looks like a really big number, but really is it? It's seconds. So it's not really a very big number. That is the amount of time it's going to take that satellite to do what? Go around the Earth. And that's not that many seconds. Just 1 second. Let me take a pause here. All right, number 17. We've got a car, 2,000 kilograms. It's going around a turn. The turn has a radius of 20, so it's like a circular turn. The road's flat. It's not a banked road like you would have like in NASCAR or something. It's a flat road. That gives us the coefficient of friction. And we want to know how fast can the car go without skidding off the road. Here's what you got to understand. When a car is going in around a curve, what makes it go in a curve? The friction between the tires and the road. The friction acts like what? A centripetal force. So this is another one of those situations where we got to take two equations, set them equal to each other. Centripetal force equal to frictional force. So let's go over and do that. So again, centripetal force equals frictional force. The frictional force makes the car go in a circle. We know centripetal force is M, E squared, R. Be the mass of the car times the velocity of the car, radius of the curve. Frictional force, you guys all know that's the fun equation. So that's the coefficient of friction times normal force. But it specifically told us this was on flat ground. On flat ground, what is the normal force? The weight of the thing. And how do we calculate weight? M times what? G.
Did you ever do something like retarded and do like a car and Jupiter that's turning your own?
Could. But here's the thing. Let's make sure we all understand this. Remember, this is just what we've been calling the fun equation. This is mu times N. But since it's on flat ground, remember, N is the force that does what? Pushes the surfaces together. If you're on flat ground, the force that's pushing you into a surface is your weight. So I want you to see something here.
Mu is the coefficient of friction.
Coefficient of friction.
You know, really, just
The masses, what's going to happen to the masses? They cancel. The mass of the car doesn't matter. Cancels out. And in this problem, we were looking for the velocity, right? So if we go ahead and rearrange a little bit for velocity, multiply both sides by r. So I'm going to write it this way. V equals the square root of rho r times mu times g. Just rearranged them. I canceled out the r's up here and then took the square root of both sides. So V equals the square root of rho. So V equals, in this problem, our radius was 20 meters. It's a 20-meter curve. Our mu was 0.7. And G is always on Earth, 9.8. And then we just do the math. So we go 20 times 0.7 times 9.8. Take the square root. And when we do, we get 11.7. And our units would be meters per second. Now, notice something though. That number right there only had 2 sig figs. So our answer should only have 2. So really it ought to be 12 meters per second. All right, but again, let's summarize what we did. The car's on flat ground going around the curve. What makes it go around the curve is friction between the tires and the road. Frictional force is acting like a centripetal force. So we took mv squared r, centripetal force, set that equal to mu times n, and then we rearranged and solved for velocity. And we got velocity equals the square root of rho, r times coefficient of friction times g. Here we go. Jupiter's 4 large moons, Io, Europa, Ganymede, and Callisto, were discovered by Galileo in 1610. Jupiter also has dozens of smaller moons. Jupiter's rocky, volcanically active moon Io is about the size of Earth's moon. Io has a radius of 1.82 times 10 to the 6 meters. And the mean distance between Io and Jupiter is 4.22 times 10 to the 8 meters. Now, we got to pay attention to these two numbers. This number right here is the distance between what?
It's the radius of
It's the distance from the center of Io to what? The center to the surface. From the center of Io to the surface of Io. That's what that number is. The second number is the distance between Io and Jupiter. So the actual radius that we're going to have to use to work this problem, we're going to have to add those two together, right? To get the actual radius that we're looking for, we want the center of Jupiter to the center of Io. We're going to need to add those two numbers together. And we'll do that in a minute. But here's what we're looking for. If Io's orbit were circular, which is what Newton's version of Kepler's third law assumes, how many days would it take for Io to complete one revolution around Jupiter? So we're looking for the period. Now, to calculate that period, we're going to have to set some things equal again. Centripetal force equal to Gravitational force. FG. Question.
That's Earth days, right?
Earth days. Yep. So we also want to find the speed. So let's find the speed first. That's an easier one to deal with. Let's find the speed first. Go on a little further. Again, this is one of those problems where we're going to have to say, okay, I realize that the centripetal force that keeps Io going around Jupiter is gravity. I'm going to set mv squared over r. And remember, that's the mass of what here? It's the mass of the moon. It's the mass of Io. So I'll put an I there, maybe. And that's got to be equal to the force of gravity, which is big G, times the mass of Jupiter, times the mass of Io, all over radius squared.
And I think we need to at least know one of those before doing. I think we need to know Massachusetts.
We do, and we'll get it. We'll get it here in a minute. So now we're going to do a little cross multiplication. We're going to try to solve for the velocity first. So we're going to multiply both sides by r. And we can see we can cancel some stuff out. This is going to cancel. It's going to cancel out that square right there. Put my line back in.
Can we cancel out one of the ends?
We can. We're going to divide by the mass of Io. When we do that, that's going to give us over here v squared. And v squared is equal to, this is going to cancel, v squared is going to equal to that. Now, we do need to know the mass of Jupiter, which was not written in the problem for a reason. In your textbook. And on the test, when we get ready to do the test, I'm going to let you put this table. And we'll talk about what you need to copy out of that table in a minute. But there's a table in your textbook on page 250. If you got your book, you might want to look at it. It gives you the masses of all the planets. It also gives you the radius of the planets. It gives you the distance from the sun. All those things. So for Jupiter, it tells us that its mass is 1.90 times 10 to the 27. That's the mass of Jupiter. So this is pretty easy math after that. We're going to put in G, 6.67 times 10 to the minus 11. We're going to multiply that by the mass of Jupiter, 1.90 times 10 to the 27. We're going to divide that by the radius. Now remember, the radius that we've got to use, it told us that the distance from the center of Io to the surface of Io was 1.82 times 10 to the 6th. And then it told us the distance between Io and Jupiter is 4.22 times 10 to the 8th. I wish it had been a little bit more exact on what it told us. What we really need to know is that distance, 4.22 times 10 to the 8th, is it the distance between the centers or the edges? And I think what we're going to do, since it's not exact, is where it says the mean distance between Io and Jupiter is 4.22 times 10 to the 8th meters. We're going to take that to mean the distance between their centers. I may be wrong here. But that's the way we're going to work it for right now. If I give you a problem that I write, I'll be much more exact in my wording in this. But we're going to say that 4.22 times 10 to the 8th meters is the distance between the center of Io and the center of Jupiter, which would be the radius we're looking for. So I'm going to put right here 4.22 times 10 to the 8th meters. And then it's just a matter of doing the math from there. So 6.67 times 10 to the minus 11 times 1.90 times 10 to the 27th divided by 4.22 times 10 to the 8th. And then we've got to take, remember that's equal to v squared. So we've got to take the square root of that as well. And we end up with this number. 1.73 times 10 to the 4th. Now, if we look at our units, we're trying to find the velocity. So we would think we ought to get what? Meters per second. Let's see. Kilograms cancel with kilograms. Meters cancel meters. You got to remember that Newton is a kilogram times a meter over a second squared. So the kilogram part of that's going to cancel. That's going to leave us with a meter squared over second squared, which when we take the square root, gives us meters per second. So that is what we're looking for there. That's the velocity of that satellite as it moves around Jupiter. 1.73 times 10 to the 4th meters per second. Now, the other part of that is we also have to find the period. And the period is the tougher part. Now, again, you could have the formula written down. And it's the formula we derived in the last problem. I'm going to derive it one more time, just to make sure you know how to get it. Another situation where we got to say centripetal force equals gravity force. M v squared over r has to equal g m r squared. Remembering that this is Io in Jupiter, and this over here is the mass of Io. Now, period's not up there right now, so we got to do a little substituting. And what we're going to have to substitute is for V. Remember that V is 2 pi r over T. So I'm hoping you see that this down here on the bottom is equivalent to that on the top. And this is where the math gets a little complicated. Let's keep working and let's move over here for a minute. Let's go ahead and square this. So that'd be 4 pi squared r squared. My marker is terrible here. All over t squared, all over r. And that's equal to g, m of Io, m of Jupiter, all over r squared. Now, last time I went through and I worked all the algebra. To save some time, I'm going to skip some of the algebra here. You can go back to that last problem and see how to do it. What you should know is that when you solve that out for t, you end up getting t equals 2 pi times the square root of what? R cubed all over g times what? The mass of the thing in the middle, which in this case is what? Jupiter. When you do the math, that's what you're going to come up with. We said that equation, what's the name for that equation? Newton's version of Kepler's third law. So let's just plug into that formula and get our answer now.
That should be a set problem to derive Newton's version.
Yeah, could be. So let's go 2 pi times the square root. Listen, please. Times the square root of the radius, which we said was 4.22 times 10 to the 8th. We've got to cube that radius all over our universal gravitation constant, G. And then multiply that also by the mass of Jupiter. And again, the mass of Jupiter is 1.90 times 10 to the 27th. Now once again, the math here is a little bit messy. Let's see if we can't simplify it down a little bit. Let's go 4.22 times 10 to the 8th. Let's cube that. Divide that by 6.67 times 10 to the minus 11. Divide it again by 1.90 times 10 to the 27th. And then finally, take the square root. And don't forget, you got this 2 pi out here, so you got to multiply by 6.28. When you do that, if you do all your math right, you should get 1.53 times 10 to the, let's see, 1, 2, 3, 4, 5 times 10 to the 5th. Now, pay attention to units. It's period. What kind of units should we get?
Seconds.
We should get seconds. So let's just make sure. This is going to be meters cubed up here. That's going to cancel with these meters squared and leave a meter. This kilogram is going to cancel with this and leave behind a kilogram. Now again, we got that Newton. Remember that a Newton is a kilogram times a meter squared all over a second squared. So if we do our math right, the kilograms are going to cancel, the meters are going to cancel, and all we're left with is what? Second squared. We're taking the square root of that. So when we do, we get seconds. So that looks like a lot of seconds. That's really not that long though, right? If we converted that into hours, wouldn't be very long. So that is the period of Io around Jupiter. What now?
That's for the, yeah, that's for the periods and days.
Oh, did it?
Yeah.
Oh yeah, that's for days. So let's convert it. To convert it, let's do a quick conversion here.
About 1.8 days.
All right, so to do the conversion, 60 seconds in a minute, 60 seconds in an hour, or 3,600 seconds in 1 hour, and then 24 hours in 1 day. So now, let's check math. Divided by 3,600, divided by 24, and about 1.77 days would be correct. So it only takes Io about 1.77 days to go around Jupiter according to our math. And that is a good place to stop.
What?
You're not gonna know.